Okay, so it's a great pleasure to be here, and let me thank the organizers for an excellent conference and a brilliant choice of speakers. I'm going to talk about M-theory and extended geometry, and it's a whole host of works, and this is a list of the collaborators that was involved in this work in various permutations. So I'll give some general motivation and introduction to things that you all know. And then I'll discuss the difference between generalized versus extended geometry, for those of you who don't know what those things are. And then I'll talk about how we can reformulate M-theory using this new extended geometry package to give us something new, and then actually get some applications of stuff that we would like. So this is a talk where we really began this work already 2.5 years ago with Malcolm Perry. And then there's a whole host of papers with various permutations of those collaborators. And there's a recent review that was just done with Daniel Thompson, and then there's another excellent review here by these people. So rather than have a long, invidious discussion of the history of the subject, let me just state the key players early on were Michael Duff, Warren Siegel, Arkady Saitlin, and that was a long time ago when they formulated what has now become known as double field theory, where T-duality was a manifest symmetry in that theory. And then this fed into the sort of E10, E11 program of Nicolai and West. And then there's key works recently by Homm, Hull, Zweibach, Park et al. Here, Daniel Waldron and Hillman, and of course Hitchin and Galtieri, who did the original work on generalized geometry. And I'm sure there's many people who've made contributions that I've not mentioned. Okay. So let's begin with perhaps what we already know and remind ourselves what M-theory is, and things which I want to point out, which I consider very attractive properties. So perhaps the most important thing is that SL2 of 2b is just a geometric symmetry of the torus. And also there's a rather nice thing that the zero brane of 2a is the 11-dimensional momentum. So these are two properties which I like very much, and that we wish to extend. And I'll explain in what way we wish to extend this. F-theory, which we've heard a lot about. Again, the SL2 becomes manifest because of just the natural symmetry of the torus. And then we allow a few more things to happen, and we can have things like 7 branes when we allow SL2 monodromies of the torus. But now perhaps there's something you're less familiar with, which is what we do when we have gauge supergravities. So it was known, of course, that dimensional reduction of 11-dimensional supergravity gives us ordinary supergravities. But then we can gauge them and get gauge supergravities, and maximally gauge supergravities were classified, and it was found that you get two sorts: those that could be obtained from 11-dimensional supergravity through a Shirk-Schwarz reduction, and that was nice. That fitted into the M-theory picture where we had a parent for all these theories in lower dimensions. But then it was discovered that there were some gauge supergravity orphans. There are a set of gaugings of supergravity which had no parent. And this was very unsatisfactory if you're a believer in M-theory, where all the theories in lower dimensions that were sensible theories should come from some parent theory up above. So one of the motivations of this talk is to generalize the properties of M-theory I've discussed, but also to fill in these question marks and potentially provide a parent for these gauge supergravity orphans, and perhaps a parent also for 11-dimensional supergravity itself. Okay. So, as I started to point out, in 2b we have this SL2 symmetry, but you know, there's the whole U-duality symmetry, which is much richer. So it was known from dimensional reduction that we could have, for example, if we reduced on a D torus, we could have an SL5 U-duality group, SO55, E6, E7, etc. And that although these duality groups were manifest after dimensional reduction, it was believed for quite some time that perhaps they were present in some way in the non-reduced theory. Okay. So one of the key things that we're going to do is M theory and F theory concentrated on SL2Z, and there are all sorts of ways to geometricize that duality group, and we're going to want to geometricize these U-duality groups for M theory, and do so without a dimensional reduction, but go the other way, like F theory did, by going up to higher dimensions. So this is our wish list, our goal for today. We want to extend and repackage M theory to make that Kremer-Julia duality groups manifest, no dimensional reduction allowed. We want the repackaging to be geometric in some sense, and I'll explain the sense in which I mean geometry. And so that's just like we have the SL2 of M theory or F theory, but now we want these other groups. And then, just like with the D0 was a momentum state in this extended theory in 11 dimensions, we want all our branes to be momentum modes in the extended space. So equivalently, there'll be no central charges in the associated supersymmetry algebra. And because I don't like having orphans, we want to find a parent for the orphan gauge supergravities. And also, furthermore, we'll allow monodromies in these in this representation, and hopefully link them to the exotic branes of Shigemori and de Boer. Just as F theory produces 7 branes, we can have more exotic objects once we allow the fact that we've got a more manifest representation of the U-duality group and geometricized it. So the great thing about this talk, actually managed to put a tick by all of these. So by now, hopefully, I've sold you that there's something here that you should be interested in. So what are we going to do to be able to achieve this? Well, we're going to have to combine the metric and the 3-form of 11-dimensional supergravity into a single geometric quantity. We're going to have to combine the diffeomorphisms and p-form gauge transformations into a single thing, which will be a generalized diffeomorphism. And this package will be the sort of generalized geometry first introduced by Hitchin that was associated to manifest T-duality, but it'd be generalized to the U-duality groups. But then further, we will extend it, and I'll explain how we go about doing that. So let's just review generalized geometry for T-duality. What Hitchin did was extend the tangent space of the theory of the cotangent space, and then have a metric, which was essentially a metric like this. So this is the usual metric, and the dual, and you can see if I set B is equal to 0, G goes to 1 over G between the two halves of this space. So this is a linear representation of ODD. ODD acts linearly on this space. So this is just extending the tangent space, but you can do better. You can extend the space itself so that generalized geometry becomes the tangent space of the extended space. So what that means is, for this T-duality space, I have to double the number of coordinates. And for the string, this is normally called double field theory, because the dimension of the space is doubled. And indeed, the origin of this came from a truncation in string field theory, for where you kept the winding modes and the momentum modes simultaneously, but threw away the oscillators. We could discuss later what sort of a truncation that is, because it's clearly not a low energy effective action, but one would hope it's some sort of consistent truncation of the theory. And the evidence is that it is a consistent truncation. Okay, so those will be the forms on the string world sheet, where you've doubled the space, that's the usual coordinate, and then that's its dual, and then that metric is what will couple to that. So the great thing is you can do the same thing for membranes. We extend the tangent space to include a sort of cotangent bivector thing. And then we have a metric that will combine for us the usual metric and the 3-form to give us an effective metric on this generalized geometry. And then we want to do the same thing again and say, okay, we've extended the tangent space. We should actually extend the space itself so that the tangent space of the extended space is associated with this metric. And this is our basic geometric package that we're going to try and rewrite the low energy effective action of M theory, i.e. 11-dimensional supergravity, using this metric. Okay, because this metric contains G and C. Okay, so we extend the space as before. Here are our coordinates. And then the next step, it's not enough that we just write down some metric, some coordinates. We want to have a dynamical theory, so we want to construct an action or Lagrangian such that when we move the dependence on the novel directions, we reproduce ordinary supergravity. But this is clearly not a duality covariant condition. It's exactly the opposite. This breaks duality by picking out some set of coordinates as being special. So what we're going to do is then construct a duality covariant condition that will allow us to reduce the theory, and then different solutions of this duality covariant section condition will yield the theory in different duality frames. So in other words, you're extending the theory, introducing an equation, a constraint, and the solutions of that constraint equation will spontaneously break to give you the duality frame. So let's be concrete and take a particular example. And the simplest case to work with here, I think, is SL5, which is normally associated with where it acts sort of in 4 dimensions. As we go up in dimension, then we need to add more and more brane wrappings. So this is just where we have membranes. So we decompose the 11-dimensional space into a sort of trivial 4-7 split. And we're just going to look at the 4-dimensional space and allow arbitrary dependence on those 4 directions, so there's not a dimensional reduction there, and see how the SL5 acts inside these 4 dimensions. So there's our usual A runs from 1 to 4, that's our usual 4 dimensions, and then now we will have 6, if you like, membrane winding modes. So then we'll have 10 total coordinates, 6 plus 4, and that's the 10 of SL5, in addition to the 7 dimensions that we're ignoring. Okay, so this would then be a 17-dimensional theory in order to make SL5 manifest. As you go up in new duality group and want to make it more manifest, you obviously have to have more and more dimensions. But let's look at this simple case for now. So then we want to write down an action, or Lagrangian, as we've done here, with completely made out of that metric. And these are SL5 indices, so this is manifestly has SL5 global invariance. And it's a full nonlinear action, and it has the following property. If I demand that Mij is independent of those winding modes, then we get Einstein-Hilbert minus field strength squared. Okay, and I say this is miraculous because when you look at what's in this M, go back, containing metric, C squared, this weird G inverse squared, and so on, it was completely unclear when we began this game that you would be able to write down an action that would reproduce the usual thing of Einstein-Hilbert in the space plus field strength squared. Okay. So far we've not done that much. Yeah. Yeah. Yes. Well, no, it's not obvious. I'm going to come. Okay, I'll come later to equations of motion, and we come up and we describe some solutions, and also relate. Maybe we can postpone this question till later when I've described some more properties of what happens.
Why did you truncate to only 2 derivatives?
Oh. Yeah, good point. That's absolutely fair enough. So in principle, if we wanted full M theory, we should have arbitrary large numbers of derivatives here. But in the end, we're going to be modest, and we're going to say we're going to aim at reproducing Einstein-Hilbert by H squared. So that's got 2 derivatives in it. Yeah. As I said, absolutely. There is no, good, brilliant. There is no low energy effective approximation here. So say now it's wrong, and then I'm going to continue, and then you're going to see the thing, and then you're going to have to tell me where the inconsistency lies. This is not a low energy effective action. It's a truncation, and then we have to justify it. And we can do various tests. So let's continue through now. So then, what are the local symmetries of this thing? Because it's not obvious what the local symmetries of this full thing is. And we want to covariantize this section condition. So we can do that in double field theory. The section condition was actually related to the level matching condition, and we can't do that. So we're going to have to be a bit cleverer, and it ties up these local symmetries with picking the section condition. So it was known, the people in generalized geometry knew that there was some sort of, the symmetry was associated with something called a Courant bracket. And already you knew that when you compose diffeomorphisms with gauge transformations, then you didn't just get something that was the same as ordinary geometry, you had to change things a bit, which is why this action is not the Einstein-Hilbert action of M. Because the Einstein-Hilbert action of M is diffeomorphism invariant, but if you just take the Einstein-Hilbert action of M, it's not P-form gauge transform invariant. So you have to construct effectively a new scalar for that symmetry. And so you can show that there's a generalized Lie derivative which acts on this space, and that action is invariant under that generalized Lie derivative. And when you restrict it in the same way, then you find it produces diffeomorphisms and gauge transformations. And then you want the algebra to close and reproduce this current bracket, but it doesn't. It closes plus some junk. And then you hold up your hands and you despair, but then you see that actually, if you obey the following condition, so this is where we've introduced SL5 coordinates, then actually the algebra closes and the Jacobi identities are obeyed and everything is fine. So crucially, the section condition, so this is a covariant SL5 condition, is tied into the consistency of the generalized Lie derivative. So just to get some intuition of that, if I now write this in terms of ordinary coordinates XA, then you get these two conditions. And this is the generalization of level matching for the membrane, effectively. And these conditions have been seen before by Obers and Pialin when they were looking at constraints on the central charges of half BPS states. You should think of this d by dy as the central charge z, and d by dxa is just the ordinary momenta. So that was for SL5. You can sort of crank some handles and keep on going. For SO55, then you need to include fibrane states. We've got usual modes, membrane modes, fibrane modes that are winding. And so it forms a 16, a spinner of SO55. And then you end up forming some hideous metric again that's very nonlinear. And you derive this using the theory of nonlinear realizations of the U-duality group. And yea, verily, it's the same sort of action, but with slightly different coefficients. So I'm not going to bore you and reproduce this for every U-duality group, but we could do it up to E7 with no problems. I say with no problems, with a great deal of hard work, but it all followed the same form. So, okay. Some things which are unsatisfactory about this is the geometry here is not very manifest. This is like writing down general relativity in terms of the metric and its inverses and its derivatives without first constructing a connection and Riemann scalar and so on. So various people have worked onto understanding this as a proper geometry, Daniel Waldron in particular, and we have also some forms. But let's just move on a little bit. So you can then also, you can go to E8, and things get a bit more involved, but there's been some progress there. And then Peter West and other people have said that actually you can keep on going, and then this is involved what's called the E11 program, we decided not to be so ambitious as do E11, but just see if we can make manifest these more finite U-duality groups. And so this is the general story in terms of what the generalized diffeomorphism is. It's related to the usual diffeomorphism. And there is something called the Y-tensor, which effectively encodes for all the U-duality groups how the symmetries change. And then the section condition is also always given in terms of this Y-tensor. So the BPS states are very interesting from this story. So essentially, they are always null states in the extended space, which is easy to see, because the momenta is equal to the Q, and Q is equal to P12, the momenta in the 1,2 direction. And this is just like how charged objects look in Kaluza-Klein theory. And so we can actually find solutions of those equations of motion, and here I've just given a simple example of SL4, which corresponds to a wave pointing in one of the extended directions. This one's pointing in the 2,3 direction. And say, well, what is this from the reduced point of view? So it was formed by actually taking a usual wave solution, rotating it using SL5 so it points in the dual direction. And then when you reduce it and look at it, it's actually the membrane. So this is in force. It's a bit sick because of the codimension, but that's not the issue. But this shows that you can actually find solutions of this theory that will reproduce for you the strings. We also did it for double field theory for strings and branes, and it extends the idea of a D0 brane being momentum in the 11th. So now you have all of your branes and strings are massless waves in the extended space. So there's no scale in the extended geometry. The scale arises, the tension arises, just like it does with a D0, through compactification, which I think is related to Nati's question about why we can truncate. So I need to have some other payoffs. Whenever we have a section condition, you can show that you always get back to ordinary supergravity. So that's lovely and marvelous, but you want to do more. And this is where what you can do is you can forget that section condition, which is like a Kaluza-Klein reduction, and instead allow dependence on the extra coordinates, but they'll become restricted in a different way. And what you do is the sort of Shirk-Schwartz trick. You introduce a twist matrix so that for a particular field with some any dependence on x and y, you say it factorizes in this form, and then you've got these what's called twist matrix W. So this is what Shirk and Schwartz did in order to get things like gauge supergravities. And then you insert this into the actions that we just described. And this was also done, I should say, for double gauge supergravity by these people. And then the structure constants of the Shirk-Schwartz reduction become the embedding tensor of gauge supergravity. And then what happens is the embedding tensor, which is this tensor which classifies how you can have the different gaugings, and it was classified, it had various constraints which were determined through supersymmetry. And those constraints just come about through things like the Jacobi of the generalized Lie derivative. And then those supergravities, those gauge supergravities, which previously you couldn't get from dimension reducing from 11 dimensions, you can get just from a Shirk-Schwartz reduction from these big extended spaces. Okay. Good. So, we can wrap up a bit. So we can construct a U-duality manifest symmetric action based on the generalized metric. We have a generalized metric for everything up to E8. We have a section condition which is duality covariant and whose solutions spontaneously break duality symmetry. So here your duality frame is just picked through a spontaneous breaking. All strings and branes are massless waves in this geometry with momentum pointing along the new novel directions, just like the D0 was a momentum mode in M theory. And our previous gauge supergravities, which were an embarrassment for an M theorist, now have a, quote, geometric parent. Thank you.
We have 5 minutes for the question or comment.
Hi. Can you make any comments about the higher derivative terms that you briefly mentioned? Because
Yeah.
when I reduce, I need automorphic forms,
Yeah.
coefficients.
So what you'd like to do is extend this so that if I could write the higher derivative terms in this form, then the higher derivative terms will be duality manifest. Now, at the moment, people haven't managed to do that. I'm not saying it can't be done, but it just requires a bit more hard work. There's a recent paper by the Gadasgar brothers where there's various comments about this. So because you've got a duality manifest form, and people for years, people like Michael Green, have been working on the fact that you can work out what your higher derivative completions are, well, you can have a go at doing that, because if you're using these objects, duality is always manifest.
Okay.
Yeah, hi, sorry, I just have a naive question. What's the story with fermions and supersymmetry?
Yeah, good. Okay, so I didn't go through the whole thing, but what I wrote out for you in that Crema-Julia list was G, and actually, this is actually a coset structure of G over H, and the fermions live in H, and those H's are always SOs, well, up to E8. So the fermions live in a spin rep, yeah, not in G. That's worked out, and indeed, Johan Hook Park has worked some of those details out.
Can you just clarify Can you just clarify for a moment the statement about the supergravity orphans?
Yeah. So there was the embedding for maximally gauged supergravity. I think it was Samtleben, DeWitt, and Nikolai went through a lot of hard work to look at what consistent gaugings there were in supergravity, and they found it was classified by something called the embedding tensor, and this embedding tensor had various constraints that you had to solve and so on. And then they through hard work, could see which ones of those you could get from dimensional reduction through Shirk-Schwarz from 11-dimensional supergravity. And then there was a clear set that you could not get from Shirk-Schwarz reductions. So I'm calling them orphans because it looked like they were parentless. Now you could then actually get some of them for sure if you allowed non-geometric compactifications. So what you do here is you have our action, take one of those, and put in the Shirk-Schwarz ansatz that I gave you, but now this is on the full space. This is, I'm allowing full dependence on the extended directions, but of a Shirk-Schwarz type, which probably means the space is parallelizable. Then you calculate, and you can sort of see it if you shove it into, I actually got an extra slide, shove it into the generalized Lie derivative, you'll get this thing X that will come out. And this X, which is in terms of the twist matrices, but twist matrices in the full extended theory. And that turns out to be the embedding tensor. And the constraints on the embedding tensor just come from things like the Jacobi constraint on this thing. So it geometrically realizes through the generalized Lie derivative that this extended theory will land you on the gauge supergravities that previously didn't seem to come from M theory or 11 dimensions.
So in the example you started with SL5,
Yeah.
the sense in which you make SL5 manifest in 7 dimensions, although...
No, I want to make it manifest in 4. Because it's acting on the 4.
Well, I would say that it's a 7-dimensional theory that has SL5 symmetry. So to really complete the story, you should add the 7 dimensions you didn't talk about.
Absolutely, yeah.
But to see SL5, you take the fields to be independent of all 10 coordinates that you described.
No. No, that's the crucial point. If we did that, we wouldn't have achieved anything new. You only need to take it, so where are we? So here we have 10, these run from 1 to 10. And there is no here, this is SL5 manifest, and there is no dimensional reduction in the sense of it depends on all 10 coordinates. Then I take a solution to the section condition.
I find the meaning of your action extremely unclear, as follows. The action is written on a 10 manifold,
Yeah.
but you haven't told us what structure the 10 manifold is supposed to have a priori, so that you can write that action. And there's no obvious answer, given the formula you've written.
Yeah. So, so indeed. So what we have to do is say that we have it really comes down to, I mean, whether you're happy producing a generalized geometry, because this is an action where we have metrics which live in generalized geometry, and then you want an action for that. And then we have, well, we have some generalized diffeomorphism, so we have some diffeomorphism structure. So what is it you'd like me to add?
I don't know what your formula meant.
Oh.
Because if literally in terms of on R10, where you've picked 10 coordinates, you can write that formula. But in greater generality, I don't know when you can write it. So Einstein action we can write on any manifold with a Riemannian metric.
Yeah.
But you are on a 10 manifold with an M field.
Yeah.
But it's not true that your action can be written on any 10 manifold with any M field.
I agree.
It needs some additional structure, and you haven't told us what the structure is.
Yeah.
So in a very narrow sense, I don't know what your formula for the action meant.
Okay. No, I agree. So, okay. If I may put it in a kind of way, what we've done here is local. And then what I think you're saying is when we have a manifold structure is how we can piece these things together.
Even locally, I don't understand your formula.
Oh.
If you picked, well, what does local mean? If you've actually picked 10 distinguished coordinates, then
Yeah.
I can't stop you from writing them.
Yeah.
I believe you are expecting, you even claim the formula is related to R plus H squared.
Yeah, yeah.
So I think you believe it has some kind of diffeomorphism symmetry.
Absolutely.
I haven't the faintest idea what it's about.
So that this action, or Lagrangian, is invariant under the generalized Lie derivatives that I wrote down. So that's a local symmetry that it's invariant under.
Which include 4-dimensional and not 10-dimensional diffeomorphisms.
4-dimensional diffeomorphisms and 3-form gauge transformations combined.
How do 4-dimensional diffeomorphisms act on all 10 coordinates? Was that clear?
You have to, I mean...
My instinct is that your formula only makes sense after dropping the dependence on the 6 of the coordinates. And yet you insisted that you wanted to write it without that assumption a priori.
Okay, so...
But I'm not convinced you've defined anything before you drop that dependence.
I mean, I can only say that you calculate this... Yeah, so I've got to obey the section condition thing, which we had before somewhere. Say this thing. And indeed, that section condition will imply that we have to drop some dependence on the coordinates, but which ones I drop is a choice.
So we're on a 10 manifold where you can write down those two equations.
Yeah.
But it's very hard for me to know what kind of 10 manifold that is.
Okay.
I think it's extremely constrained, more than you would want, so I think it's a crucial point.
Yeah.
Okay, so time is up. So let's thank David again.
Okay.